In this segment, we will derive the formula for the longitudinal coefficient of thermal expansion of a unidirectional lamina. We will not be deriving the formula for the transverse coefficient of thermal expansion. We'll do that in a separate module. And let's go and see that how we're going to go about doing that. So this is the formula which we'll be deriving in this particular video, and this is a formula for the transverse thermal expansion coefficient, which we'll develop in a separate video. So what is alpha 1 and alpha 2? It is basically that if you have a fiber and matrix in a unidirectional lamina, then this is fiber, this is matrix, this is called direction 1, that's the longitudinal direction or the direction along the fibers, and this is the transverse direction, which is the direction perpendicular to the fibers. So we're going to calculate this, but the reason why I wrote both of these formulas here is because the formula for alpha 1 and alpha 2 is not a simple rule of mixtures or inverse rule of mixtures. It is here you're finding out that, hey, it does not only depend on the thermal expansion coefficient of the fiber in the matrix and the volume fraction of the fiber in the matrix, but also on the Young's modulus of the fiber in the matrix. And when you look at the formula for alpha 2, you also getting the value of the Poisson's ratio of the fiber in the matrix involved. So before we start calculating alpha 1, let's review a little bit of what we have learned in our mechanics of solids class. Let's suppose I have a rod made of steel, and let's suppose the length of this rod is L. If I heat it up through a temperature of delta T, then I know that this rod is going to expand, let's suppose, and this distance is, let's suppose, delta L. And then in that case, we know that delta L will be equal to L times alpha times delta T, because that's how we define our thermal expansion coefficient, change in length per unit temperature, right? So if I want to do delta L by L, that goes alpha times delta T, but this is the definition of the strain itself. So we can also define alpha as the strain per unit temperature, longitudinal strain per unit temperature. Now, why are we showing this is because of the fact that we want to be able to see that, hey, when does a mechanical stress occur when we have expansion taking place? So let's suppose I have this rod which is set to be fixed on this side, and let's suppose I put a wall here. And let's suppose this wall is a distance of delta A from the edge here when the length is L before it's been heated up. Now what's going to happen is that if delta L is greater than delta A, then what's going to happen is that you will have mechanical stress. If delta L is less than delta A, then there's going to be no mechanical stress. Why? Because it is not going to touch the wall. So only if the amount of expansion which is going to take place is going to be more than the space which is here between this edge and this edge right here, it's going to touch the wall and hence try to expand a little bit more, but it can't. So there is going to be a strain caused in this particular rod, and hence there will be mechanical stress caused simply by expansion. So what we mean by that is that the displacement, which is called mechanical displacement, will be, hey, whatever is the actual displacement taking place, which in this case is delta A, you subtract from that what would be the displacement which would have taken place because of free expansion. So let me write it down, fully free expansion. So if I divide this by L, I divide throughout by L, this actual divided by L, delta free expansion divided by L. What I'm going to find out is that, hey, I'll find that this epsilon mechanical, that is the mechanical strain caused, will be equal to, hey, whatever is the actual strain which you are seeing with your naked eye, minus what is the free expansion delta? That is this one, L times alpha times delta T. So that will be alpha times delta T. So what you're basically seeing is that the mechanical stress is caused through the mechanical strain, which is caused by how much it actually strains and how much it would have strained if it was allowed to expand freely. So it's a very important concept, because what's going to happen is that in a fiber matrix environment where you are combining fiber and matrix, the fiber is going to try to expand some, the matrix is going to expand some, but they're not both going to expand the same, want to expand the same amount. They were free to expand because the thermal expansion coefficients of fiber and matrix are different. So there's going to be an actual strain which is going to take place, which won't be same as the free expansion strains, but also only some of that actual strain will contribute to the mechanical strains and hence the mechanical stresses. Let's keep that in mind, and then what we'll do is we will look at the derivation and be able to think more about it. Let's go and we show the diagram again for the unidirectional lamina right here. So we have this unidirectional lamina. This is direction 1, this is direction 2. And then so 1 and 2 are the directions, right? And then you have fiber, matrix, and composite. That's what F, M, and C will stand for. So this will be our notation. So the first thing which you have to recognize is, let's suppose this lambda was a thickness T, so we're going to keep it there. The first thing which you have to recognize is that the strain in the fiber in direction 1 will be same as the strain in direction 1 for the matrix. It will be same as the strain in the whole composite in direction 1. Because if we're going to expand, if this edge is going to expand, this edge is going to expand the same amount in the fiber and the matrix, and hence the overall composite also. That's all we are trying to say here. It's not like somehow the fiber is going to shoot out or shoot into the matrix. No, they are going to expand the same amount. Now we know that the strain in the composite will be equal to whatever is the alpha 1, which is the thermal expansion coefficient of the composite, multiplied by delta T. That's what epsilon C1 would be. So the question is that, hey, how can we find this alpha 1 based on that, hey, we know that this is the strain in the composite, we know the strain in the fiber, matrix, and composite is the same. How can we use this information to be able to go forward? So the first thing is that the stress in the fiber will be equal to the Young's modulus of the fiber times the strain in the fiber in direction 1, and that will be the mechanical strain. So what is the mechanical strain? Mechanical strain will be, hey, whatever was the strain in the fiber, actual strain in the fiber, minus whatever would have been the free expansion strain in the fiber. But we also know that since the strain in the fiber is same as the strain in the matrix and strain in the composite, this is nothing but alpha 1 times delta T. So that makes it very simple here. Now let's go and look at the strain in the matrix, stress in the matrix. The stress in the matrix will be equal to the Young's modulus of the matrix times the normal strain in the matrix in direction 1, the mechanical part of it, right? And what would that be equal to? That will be equal to, hey, whatever is the actual strain in the matrix in direction 1 minus alpha m times delta T, because that's the free expansion term, and this is how much it actually strains. But we also know that this is going to be equal to alpha 1 delta T, because the strain in the matrix in direction 1 is same as the strain in the fiber in direction 1 and is the same strain as in the composite. So that's why we're able to do this. So now what we have is an expression for the stress in the normal stress in matrix in direction 1 and the stress in the fiber, normal stress in the fiber in direction 1. How can we relate these things which we have already said and now to be able to find out the expression for alpha 1? So that's what we're going to do next. So if you look at the force in direction 1 will be equal to 0. That's the force, overall force in the composite. Now, what is the force in the composite? The force in the composite will be equal to, hey, whatever is the force in the fiber and whatever is the force in the matrix in direction 1. So that will be 0. What is the force in direction 1 will be the stress which we have in direction 1 times the area of the fiber. The stress in the matrix in direction 1 times the area of the matrix will be equal to 0. However, what we can do is we can write it in terms of fiber volume fraction by multiplying this by t, multiplying this by t, and multiply by t here. Then we divide by the area of the composite times t, that's the volume of the composite. Area of the composite multiplied with the thickness of the composite divided by ACT. So this is going to be 0 anyway, but you can very well recognize that, hey, this is the volume fraction of the fiber and this is the volume fraction of the matrix. So the stress in direction 1, normal stress in direction 1 of the fiber times the volume fraction of the fiber plus the stress in direction 1 of the matrix times the volume fraction of the matrix will be equal to 0. So now we have this expression, so things are looking good, because now what we can do is we can substitute the expression for sigma f1 and sigma m1, which we wrote in terms of the Young's modulus of the fiber in the matrix and the free and actual strain terms, and we'll be able to get the expression for alpha 1. So let's go and see how we're going to go about doing that. So we already found out that EF times alpha 1 delta t minus alpha f delta t is the stress in the fiber, right? Then we multiply with the volume fraction, and then plus this is the normal stress in the matrix, alpha 1 delta t minus alpha m delta t times Vm will be equal to 0. So that's what we're getting by saying that the overall force in direction 1 is equal to 0. Now you can see that, hey, you can separate out the terms. So what we can do is we can just get rid of delta t, because that we can divide by delta t on both sides. We'll be able to get rid of it. And what we're going to do is we're going to collect the alpha 1 terms. So if I calculate collect the alpha 1 terms, this is what I get. I get EF VF from here, and then from here I get EM VM, right? And then I take the rest of the terms to the right side because I'm trying to find alpha 1. So I'll get EF alpha F VF plus EM alpha M VM. So this term here is going to go to the right side, this term is going to go to the right side, and that's what I'm going to get there. But I know that, hey, this is nothing but E1, right? That's the formula for Young's modulus in direction 1. So I get this. So once I have that, I can now write down the expression for alpha 1, which I had on the second slide. So we have basically derived the expression for the Young's modulus in direction 1. And again, keep in mind that what we have said here is that the thermal expansion coefficient direction 1 is not a simple rule of mixtures where it is only dependent on the thermal expansion coefficient of the fiber in the matrix and the volume fraction of the fiber in the matrix, but also on the Young's modulus of the fiber and the matrix. And that is the end of this segment.